Hello guys, welcome to another video, and in this video we are going to try to find out some of the properties of moment generating function and characteristic function and stuff like that for the Poisson distribution. And obviously we'd be trying to look forward to what we have learned in the previous sections, including the first moment, the second moment, the third moment, higher moments, which we also call the bell numbers. So in the last video we did a lot of things, but in this one we would try to focus a bit on the part of MGF, or what I call, this is the MGF. This is called the moment generating function. So we are going to study this. Okay, so the MGF, let me define it properly first for the discrete case, and then I can define it for the continuous case, and then we can get on to with it for different distributions and for different parts. Okay, so since this I'm covering MGF for Poisson distribution, I might as well cover it for general distributions as well. So this might be a long video, but we are going to learn it completely. So what is MGF? MGF is a function which gives us an infinite series of moments okay. So MGF is basically an infinite series of moments. So how do we define it? So for RVX, if its PMF is probability of x, then, so let's say this is the PMF, that is the PMF function, probability mass function, then the MGF is defined as mx t equals to summation, take a small y over the whole sample space. And what you can do is, we actually need to find out the expectation of e to the power tx. So what we do is we do this into probability of x y. So this is the MGF in real terms, where t is obviously a real number, a parameter. It's a parameter which we used to find, but we do not really need this parameter. So in general words, the moment generating function is just the expectation of e to the power tx. E to the power tx is basically the expectation of which we call the moment generating function, and this definition is true regardless of if it is a discrete random variable or it is a continuous random variable. Okay, so let us try to find some examples here so that we can understand what's going on in a much more better way. So firstly, let us do it for the Poisson distribution, because this is important. In the discrete case, the Poisson distribution is very important, and obviously the MGF of it is also important as well. And we shall see how to derive the moments from MGF in a much more similar way, and we would know that how the MGF actually helps us to find the PMF or PDF of joint distributions easily than we could have hoped, because it really is a very useful tool. So what is the Poisson distribution? We know that let x be Poisson of lambda, then the PMF is probability of x equals to k e to the power minus lambda to the power k divided by k factorial for k equals to 0, 1, 2, ... right? So this is the Poisson distribution. Now since this is a Poisson distribution and we are interested in finding the MGF, we can see that the MGF is, as I told you, the MGF is denoted by a capital M. We give in subscript the random variable for which we are finding the MGF, and we denote a parameter t, and it is given by the expectation of e to the power tx, right? Now, by the law of unconscious statistician, that is the Lotus Rule, we can see that this is basically equal to k equals to 0 to infinity, that is summing over all the values of the random variable, e to the power tk into the probability, which is e to the power minus lambda, lambda to the power k divided by k factorial. So this basically is the definition, and we can simplify it further as follows: k equals to 0 to infinity, e to the power tk, lambda to the power k, e to the power minus lambda divided by k factorial. Since e to the power minus lambda is a constant, we can bring it outside to find that this is essentially equal to lambda e to the power t whole to the power k divided by k factorial. And as we know the Taylor series for e to the power x is, since I have not mentioned it in this lecture, so I'm going to just write it down once again. E to the power x is basically for all x belongs to real. Then the above moment generating function would be mxt is e to the power minus lambda k equals to 0 to infinity lambda e to the power t whole to the power k by k factorial, and this thing becomes e to the power lambda e to the power t, and in all we get e to the power lambda into e to the power t minus 1, right? This is the moment generating function, right? Also what we see here is the moment generating function can be differentiated in order to find the moments. Why is that true? We shall prove it right now. So firstly, consider that mxt is equal to expectation of e to the power tx, right? Now expectation of e to the power tx in normal ways is basically equal to, let's say, k equals to 0 to infinity e to the power tk probability of x equals to k, right? Now if we were to differentiate this moment, this function which is a function of t, right? If we were to differentiate it one times, what would you get? You would get this equals to k equals to 0 to infinity k e to the power tk probability of x equals to k, right? And therefore if you put in the value 0, what you get is this. Which basically is the first moment, isn't it? So in general, since it's the exponential function, if you differentiate it n times, what you get is this. So differentiating n times and putting 0, what you would get is k equals to 0 to infinity k to the power n probability of x equals to k, which basically would be the nth moment, right? Now we find out that for the Poisson distribution case, now let us see if this actually works, because we would know if it works, because as we have already found out the moments by hand in the previous sections using the method of infinite series. So let us see. For Poisson distribution, we have that So therefore let us find the three derivatives first, and then we shall move on to find the moments. The first derivative here would be d dt of e to the power lambda e to the power t into e to the power minus lambda, right? So e to the power minus lambda is a common, so it can be taken out of the differentiation, and what we get is this. Now this differentiation would be, firstly we would write out e to the power lambda e to the power t multiplied by lambda e to the power t. This would give us lambda outside e to the power t minus lambda plus lambda e to the power t. This would be our entire expression here, right? So this is the first derivative. The second derivative would be just the derivative for the derivative of the first derivative, right? The derivative of the first derivative is lambda e to the power t minus lambda plus lambda e to the power t. Since lambda is a constant outside, it can be taken outside of the differentiation term, and this becomes lambda into d dt of e to the power t minus lambda plus lambda e to the power t, and this also becomes lambda into e to the power t minus lambda plus lambda e to the power t into 1, and since this e to the power t minus lambda, so the differentiation of t is 1, lambda is 0, and lambda e to the power t is differentiation would be lambda e to the power t. So this should be our required answer here for the second derivative. Now the third derivative, again we can just write it out in a clear way like this. Lambda squared e to the power 2t minus lambda plus lambda e to the power t. Now the third derivative would just be the derivative of the second derivative, right? And the third derivative can be found as, so this term we already did. This is basically the second derivative. This is basically the first derivative which we differentiated to find out. So the answer for that would just be this whole thing again. So we already have lambda e to the power t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t. This would be the answer only for the derivative of the first term, because this basically is mx derivative t. And for this term, the next term, we have lambda square into d dt of e to the power 2t minus lambda plus lambda e to the power t. So simplifying, what we get is mx triple dash t is equal to, let's write it below so that we have more space, lambda e to the power t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t multiplied by 2 plus lambda e to the power t. So this gives you the third derivative as well. Now it's time to check if the moments match. So E of x should be equal to this, right? So what is this? Let's go back and check. This should be this thing, lambda into e to the power t minus lambda plus lambda e to the power t with t at 0. So this should be lambda e to the power 0 minus lambda plus lambda e to the power 0, which is lambda e to the power 0 minus lambda plus lambda, which is lambda e to the power 0, which is lambda. So this one is correct. The first moment is in fact correct. Now the second moment. Second moment is basically given by mx double dash 0, and this is this part. So we can write it as lambda e to the power 0 minus lambda plus lambda e to the power 0 plus lambda squared e to the power 0 minus lambda plus lambda e to the power 0. This gives you lambda e to the power 0 plus lambda squared e to the power 0, which gives you the answer as lambda plus lambda squared, which is also correct for the second moment. And for the third moment we have as we can see above, the answer is this. So we already know the first two parts give you lambda plus lambda squared, and let's do the last part, which is this one. This is lambda squared into e to the power how much? 2t minus lambda plus lambda e to the power t into 2 plus lambda e to the power t. So 2t minus lambda, so 0 minus lambda plus lambda e to the power 0 into 2 plus lambda e to the power 0. This gives you lambda plus lambda squared into 2 plus lambda, which gives you lambda plus lambda squared plus 2 lambda squared plus lambda cube. This gives you lambda cube plus 3 lambda square plus lambda. So the expectation of x cube is lambda cube plus 3 lambda square plus lambda, which is also correct as we have found in our previous explorations. And we can see that how the moment generating function is so much useful in order to find moments of different genres, right? So this completes it, and we shall explore about the moment generating function in detail with the characteristic functions in the next sections as well, where we are going to need a little bit of integration first in order to understand the continuous random variables that we are going to get into, and later we would be coming back to the geometric distribution and different kinds of discrete distributions, because those require like special attention. So we actually need some basic info on infinite series and integrals before we can jump into the higher sections and advanced sections, just as a footnote. And before that I would also be able to use some problems on continuous random variables after I introduce them. So in the next lecture we shall do a basic footnote for integration and summation of infinite series. So that would cover like 3 to 4 videos, but hopefully that would cover at least how much we need to understand at this point right now. Okay, so thank you for watching this video. I'll see you in the next video, and do not forget to check the description for the Breatter Maths app. It's a maths app where you have all the lectures and notes regarding the video solutions also, which I'm giving here. The lecture notes for this in written theory is also available there. Please do check out. Thank you.